substance is liquid-like and the consistency at rest is like a paint. You see, rather than creating a splash, this heavy object is bouncing off the surface. Okay, so as if the force is transforming this system into a solid transiently. Okay, and same principle allows one to run across a pool of cornstarch. You can see like many YouTube videos. So this compressive force is not a requirement. One time people thought that it is the compression that solidifies the system. Actually, there is one interesting video that one guy got inside this pool of cornstarch. He has a difficult time getting out. See, that means it can resist the extensional force as well. Okay. So few years back we studied this problem in a more systematic manner in the lab, like all kinds of jamming under compression and compression under extension, and we showed that actually basically why this is so common and works for any kind of deformation, because this jamming is basically shear induced. As long as you have velocity gradient inside the system can jam, and this we demonstrated more clearly. Like you take a beaker, that is this glass beaker, okay, you keep dense suspension, cornstarch and water for example, and you have a inner cylinder that can spin very fast. Okay, so you see that so now by spinning the cylinder you can create a velocity gradient without any compression or extension. You see like the shear can actually solidify the system, and if you stop shearing, it becomes goes back to initial fluid-like state. Okay. So due to this interesting property, these materials are being used as in various designing flexible shock absorbers. These are few examples. So you take this Kevlar fabric, which is the material we use for making this stab and bulletproof vest, and you treat it with dense suspension. You see like it becomes very tough. It cannot be punctured without compromising the flexibility. That is important, because you can argue that why not a steel plate, because it won't be flexible and it can bounce off bullets and all, and also you can see it is deflecting of a hunting arrow, which is like almost more powerful than a bullet probably. Okay, and there are other potential applications as summarized in this recent review. Okay, particularly in the field of designing flexible shock absorber. Okay. So now, despite of this study, there are many open questions. For example, actually the mechanism for shear-induced jamming is not well understood. So the questions like what sets the upper limit of the stress response after perturbation, how quickly one can get to the jammed state. Once the jammed state is formed, how quickly it can relax. So if you realize, like such questions are also very important for application perspective, because if you want that, okay, some solidification required over within this time scale, so all these questions become very important. So in this, here I'll tell you about this shear-induced jamming under transient perturbation that is relevant for the examples I have just given. And I'll particularly focus on microscopic particle scale dynamics that is giving this relaxation of shear jammed state that has not been explored before. Okay, so just I'll take a step back. Now, how do we quantify experimentally such materials? So we use a technique called rheology. So you take, for example, you confine your system between two plates, and you apply some force, shear force on top on one of the plate. In this case, it is the top plate. So now you can define these two quantities, the stress and shear rate. Stress is simply the shear force divided by area, and the shear rate is the steady state velocity that is produced as material response divided by the gap. Once you know this quantity, the ratio is viscosity. So different materials like, for example, water, oil, honey, they have different viscosity. But one important thing is they are all Newtonian. That means that their viscosity is independent of how much force is applied to measure the viscosity. Now coming back to dense suspension. So dense suspension is quantified by the solid volume fraction. Now at very high volume fraction, typically approaching random close packing for Hertz-Sphere system. For example, if you have interactions, it can go down. So it becomes highly non-Newtonian. That means the viscosity now becomes force dependent. So this is a illustration. For example, for the same system, I am going to tell you that when your volume fraction is fairly small, 0.45, 45%, you see that the behavior is almost Newtonian. There is some increase in viscosity at high stress, but as you increase the volume fraction, you see very strong increase in viscosity and also some decrease in viscosity at low stress. So this is highly force dependent. Okay, so in the steady state, like how do we understand such response? The reason is the following. So this shear thickening or shear jam system, these are well dispersed systems. So you have high density of particles, but they are well dispersed. Now contact between the individual particle at rest, those contacts are weak, and those are lubricated contacts. Now as you increase the applied stress, shear stress for example, so some of these lubricated contacts transform into frictional contacts, that is indicated by red, and finally, like at high enough stress values, you have enough frictional contacts between the particles, so average number of contact is very high, and so the viscosity can increase or it can go to even solid-like state. And this evolution of contact for a wide range of system is given by this given by a model proposed by Mike Katz and Matthew Weird. It basically tells like how the force is transforming, what fraction of contacts are transforming into frictional contact under force. Okay. However, one thing is there is no information about the dynamics of contact formation or relaxation. We know that, okay, if you have so many contacts, this will be the stability, but how the contact is formed or how the contact is relaxing, that is not there in the model. So now what we study is a dense suspension of polystyrene particle dispersed in a non-evaporating solvent, that is polyethylene glycol. And these particles, since we require large amount of particle, we synthesize these polystyrene particles, which are like around 2.6 micron with a fairly small polydispersity, about 5%, in the lab by a technique called dispersion polymerization. So we make the dense suspension out of them. Now what is the experiment? We again confine the system between two plates of rheometer, and we apply a transient perturbation in the form of this step. We apply a step strain, and then we observe the stress relaxation in the system. So this is the result, what we get. So you see very fast you get to a fairly high peak stress, and the stress relaxes. Now these are for different amount of step magnitude. As you increase step magnitude, it is the peak stress increasing, and also the relaxation time increases. So and the feet, these are strong. This relaxation is strongly non-exponential. So we tried various functional form, but we found that for different volume fraction, this is for volume fraction of 58%, if I remember correctly. So for different volume fraction and strain values, this is the most general form we can fit the function. This is a power law cut off by this stressed exponential, or rather compressed exponential, because beta value, most of the cases we find it is bigger than 1. Okay, so similar functional form is observed in simulation for dense frictionless system close to jamming in these papers, but their connections are not very clear, so this is what we have tried. Now one thing I'd like to point out that now if you go to higher value of strain, a very interesting thing happens that you get to high value of peak stress, but then you develop this two-step relaxation. Basically you can see that this step is quite significant, almost one order of magnitude. Some at higher volume fraction it can be even more. So this is a log scale. So if this axis is linear, actually this is the most significant relaxation. Most of the stress relaxes during this step. Okay. So we can define two time scale. One is starting like up to the first step that we call the first time scale, and second one over which starting from this point when the stress relaxes to almost zero, we call that slow time scale, tau s. Okay, so this is the same data basically. So here I am showing the two-step relaxation separately for different strain values. One thing I would like to point out that this is the first normal stress difference. So what is that? So you are shearing the system this way. So you are measuring the shear stress, but because it's a complex system, it can develop some force perpendicular to the shearing direction also. It can be like compressive, it can be positive or negative, the normal stress. So typical signature for shear thickening system, which is very close to random close packing, it gives positive normal stress under steady shear. But here if you look at the normal stress response, you see when the shear stress is very high, the normal stress is not that high, and it is actually random. For different volume fraction it can be close to zero and so on. But when the shear stress drops, you see like there is a peak in the normal stress, there is a second peak developed. So that's why this transient response is quite different from the steady state one, because in steady state the normal stress and shear stress response for this system, they go hand in hand. Actually as shear stress increases, normal stress also increases. Just to illustrate the difference, that transient response is quite different. Okay, so now how do we understand further like this complex relaxation process in the system? Okay, so one property of this shear thickening dense granular system is like I told you about the normal stress. The normal stress in this case is generated because as you shear the system, you have to maintain some velocity gradient. That means different layers of particles, they have to go over each other. In the process, in that dynamic condition, there is an overall soiling of the pack. This is called a mechanism called frustrated dilation, and so it is soiling not only in this direction, in all direction. Now this side you have plate, we cannot see anything, but this side you have this suspension which is like it has some solvent, and this is the air, so solvent air interface. So you can see that as we shear it, the particles dynamically protrude out. So these are granular systems, so this gap between the plate is about a millimeter, and the particles are fairly big, like it is around 120, 130 micron in diameter. Okay, so this soiling or dilation competes with the air liquid surface tension, and what it results in is change in surface texture basically. Okay, so this is one aspect, and there was earlier study by Brown and Jaeger. So they showed that for a wide variety of systems showing shear thickening and jamming, this surface tension provides a confining stress. This gamma is the surface tension and A is the diameter of the particle. So they found that this maximum stress one can obtain by shear thickening is given by this gamma divided by A, but it is not exactly that. There is a prefactor of 0.1. Okay, so although the data is fairly scattered, but you can see there is a rough trend in the data. Okay. Yes.
The sample between two plates.
Yes.
So where is the air liquid interface?
So at the edge of the plate.
Just at the bottom.
Yes. Yeah. So this is the actual experimental setup, schematic of the actual setup. So you have this top plate. Actually, it is a cone because of the reason I can tell you later. And cone with very small angle, and there is a bottom plate. So we are using a counter rotation. The plates are like rotating in opposite direction. So these particles are opaque, so the suspension looks whitish. So what we do, we illuminate the boundary and we capture the image with a camera. So this is the actual setup in the lab. These are the two plates. So you put the sample and bring down the plate to confine the sample. Okay. So because we are driven by the fact that we are expecting that when this jamming happens, there will be some change in surface texture. That's why we are having this kind of experimental setup. So see what we get basically. So this is the top plate and this is the bottom plate. Scale bar is 100 micron. So you see this is the static interface. It looks like how it looks like. So after this step shear, you see that these white spots developing and they quickly disappear. Okay, and then see like there is this brightness is gradually changing. Okay, so I can play the movie. I can go back. Yeah, once more. So these white spots. So these white spots are, we call it plastic center, and this brightness that we are getting, this is due to dilation, which is relaxing also. Okay. So now why we call the white spots as plastic center? Because what we found is like if you apply sufficiently high stress, these white color spots, if they merge, they form this line and eventually that creates a fracture. Okay, so that means like the individual ones, they might be like small local plasticity. So one problem is like, see, we can see the particles as it will be clear in the next movie, only when they dilate out. After like stress drops, the particle goes inside the bulk, it is difficult to see. So this is again the same movie but with a better resolution where you can see the individual particle. You can see that there are these plastic centers near the peak stress and the plastic center goes away after the first step. But the other particles, it takes longer time before the intensity drops to the initial value. Okay. So now what we did, we tracked many such bright spots, for example this one of these spots, and plot their intensity as a function of time. And also we study the intensity variation in other region which doesn't have a bright spot, but it is the brightness just increased due to dilation. Okay, so for example a region like this. So you see like where this bright spot is there, the intensity relaxation shows as two-step behavior, right? There is a first step and there is a second step, whereas for the other region, it takes a single step, single relaxation, and we define two time scale. One is this tau p, because these are the plastic center relaxation time, the first step, because I told you that after first step the bright spots are gone. And second relaxation is the dilation relaxation. So we track many such spots and we can get a distribution of time, and you can see there is a clear separation that plastic center relaxation is happening over much shorter time scale than the dilation relaxation time. Okay. So one more thing we did, it is based on the difference image, what it is telling us. So suppose you have some image of the boundary. Now you take at some time, image is taken at certain time, and then you take image of the same region at a different time, delta t. So time difference between them is 16 millisecond in this case. So the idea is, if we subtract one image from the other, if these images are different, then you get some intensity in the difference image. That means that there is some rearrangement has happened. Suppose this image is completely static, then if you subtract the same image from it, then you get zero intensity basically, because you are subtracting same thing. Okay, so same thing we do with almost similar time separation, but during dilation, you see this absolute time is little larger. That means it is beyond the first step actually. So we calculate the difference image. So these are the images. So you see that during the plastic center relaxation, if you take a difference image, you get very localized rearrangements as shown by these bright spots. There are some small rearrangements happening, but these stands out basically. Whereas during dilation relaxation, if you take difference image for almost same delta t, you see that you get a system spanning relaxation, because everywhere this difference image is showing bright spot. Okay, so everywhere the reorganization is happening. Okay, so now we compare this time scale that we obtained from the rheological measurement. Remember, like I indicated this fast and slow time scale based on the stress relaxation data, and also we defined this time scale for plastic center relaxation and dilation relaxation. So now for wide range of volume fraction showing this shear thickening and jamming, you see that the fast relaxation that is obtained from stress relaxation from bulk rheology measurement, it matches exactly with the plastic center relaxation, the fast relaxation process, whereas that slow relaxation time matches well with the dilation relaxation time. So we get very good agreement between these two. So this indicates that fast relaxation is due to localized plastic center relaxation, and slow relaxation is coming due to system spanning dilation. So to verify this further, what we did, we also changed the solvent viscosity. Okay, so we are using the same volume fraction, but PEG, it's a short chain polymer basically. So depending on the molecular weight of polymer, you can increase or decrease the viscosity. So you see that, oh sorry, so this nothing has been, okay. So this fast time scale, this is independent of solvent viscosity, whatever variation we could achieve. Whereas dilation relaxation, with increasing solvent viscosity, the slow relaxation time increases also. Okay, and together with the last plot that I showed, so we concluded that this slow relaxation time increases with increase in solvent viscosity and particle volume fraction, whereas fast relaxation time is pretty much independent. So it supports the fact that plastic center relaxation is coming from localized events. Okay, where this average property like change in viscosity or average number of contact doesn't matter much, whereas the slow relaxation time, it depends on system spanning events, so it will be sensitive to change in viscosity or average number of contacts, because this fast relaxation time, it is more sensitive to local environment. Okay, so Pawan, how much time?
You have 14.
Oh, okay. Okay, so now one thing is like I mentioned that for this dense suspension, the steady state behavior is sort of well known. So we tried to see, like we got different type of relaxation, like I showed that there is two-step relaxation, and for small step height or small peak stress values, there is continuous relaxation which is given by stressed exponential multiplied with a power law. So now what we'd like to do is like what is the steady state shear jamming prediction for this system? So what we do, we write the suspension viscosity is a standard form for jammed system. This is called Kraiger-Doherty equation. So it is telling that if your volume fraction is very high, approaching phi j, so eventually you get a diverging viscosity as the system solidifies basically. So now what we do, we just write viscosity like sigma divided by gamma dot, and we get an expression from gamma dot, and then we consider the non-trivial solution for gamma dot is equal to 0, that is given by jamming. One trivial solution is sigma is equal to 0, because if you don't do anything to the system, nothing will happen. But non-trivial solution will give phi is equal to phi j, and using again Watt-Katz model, that is given by this fraction of frictional contact, this f of sigma for a given stress sigma. So we can get a relation between stress sigma and the volume fraction, beyond which the system will jam, and all these parameters we estimated from experiments from steady state flow curves. So this is the shear jamming boundary. That means so for very high volume fraction you have isotropic jamming. What does it mean? That means your volume fraction is so high that the system is solid anyway, you have put so much particle. This region is not accessible for experiment. Now this shear jamming, it is telling that you can, at low stress you can start from a liquid like state, but if you increase the stress it will enter a solid like state that we are interested in, and this is the boundary. So it is telling that if you are below 56% you can never hit the shear jamming transition. Now on the steady state shear jamming diagram, we just superpose the nature of relaxation that we reported, because we didn't expect any connection between these two, but looks like something is there, in the sense like inside this shear jamming boundary, this green region, we get that the form I showed you, this power law cut off by stressed or compressed exponential. So that is this green region. Now if you go to higher value of stress, in the red region you get two-step relaxation, and you see plastic center in this region, because in green region if your stress is not so high you don't see any plastic center. Okay. And interestingly, below this shear jamming boundary, we found that you can feed the data fairly well just with a stressed exponential function. The functional form completely changes. Okay, so this is interesting. We don't know like what is the basis of this difference yet. So last thing I wanted to tell you is see, for wide range of volume fraction, we found that this top boundary beyond which two-step relaxation comes and plasticity comes, this is fairly flat, and the stress scale is given, like in our case we got this 16 kilopascal approximately, except for the fact that for very, for lower value of phi, but still inside the shear, so there is some deviation, but apart from that, like in these region it is fairly flat, and you get 16 kilopascal. Interestingly, this 16 kilopascal you can get from the ratio of this PG as surface tension, which is 50 millinewton per meter, and particle diameter in our case is 2.6 micron. The ratio of these two gives you this stress value. So now looks like there is some connection with the confining stress, which is not unreasonable, because you can imagine that what is plastic center, how we see it. So what we found is like these bright spots are like excess protrusion actually. In these region the particles protrude out more, so they scatter more light and so on. So now you imagine you have some very less modulation of the interface. So this side you have suspension, the other side you have air. So imagine you have very less modulation, but near a plastic center, since the particle protrudes out significantly, you have a very, very sharp curvature, which is the radius of curvature is of the order of A, the particle size, then the stress you get, like at least this much stress you have inside your system, that is that's why the particle is pushed out so much. Whereas remember the steady state case I showed you, they found that the stress, the peak stress is given by this 0.1 time gamma over A, because in steady state you expect that much less modulation of the interface. Why? Because if you have plasticity, that is one advantage of transient measurement. If you develop plasticity and if you keep on shearing, eventually immediately your system will fracture. So that high stress scale is not possible to access using steady state rheology, only transient rheology you can. So this is something new, we are still thinking about it, but we used smaller size particle and we found that this indeed this peak stress scale goes up, so we are probably on the right path, but more work needs to be done. So now I'd like to conclude. So we showed that there are two distinct transient stress relaxation regime in shear jam dense suspensions. Okay. Using in situ boundary imaging, we showed that this localized plasticity gives rise to fast relaxation, whereas system spanning dilation results in slow relaxation in the system. And we have also indirectly confirmed such mechanism by changing the solvent viscosity and so on. And there is some interesting correlation between transient relaxation and the steady state shear jamming flow curve. So we'd like to understand better that why there is a correlation with this boundary that is predicted from steady state rheology basically. And so I didn't show anything, but if anyone is interested, I can discuss. We are finding, we are finishing up the experiment, very interesting memory effect in the system, because the idea is like memories are like we study memory effect in glassy systems and all, because out of equilibrium system they typically show memories, because equilibrium state, it doesn't have any memory of how the equilibrium is reached. However, this system we found that okay, so you apply some force and then it relaxes, the stress is completely relaxed as the system goes back to liquid like state. And we'd like to think that liquid like state will not have any memory. Whatever you did, it is erased because it has reached some liquid like state. But apparently it is not. Like if you load the system again and again, it can show some interesting trend, which is very non-intuitive, I would say. And we also confirmed this by imaging and so on. So now these are the future directions. So now one question is like, what is the nature of this plasticity? In our case, we define plasticity like I told you, that this is the bright spots that is eventually like leading to fractures. So we are like kind of concluding backward that maybe these individual ones are localized plasticity. This is not a formal way to define plasticity. Plasticity in glasses and all, you have to calculate the mean squared displacement and larger mean squared displacement. But unfortunately, we cannot see the particle for longer time. Probably one can index match and do some confocal imaging to get better understanding. But now we did some experiments which might reveal something interesting. Is like so suppose this is the force chain structure for the shear jam state, which is like there are so many contacts, the particles are constrained, it gives rise to a solid like state. So now actually we think that this plasticity is coming due to the buckling of this force chain. Why is that? Because of this experiment, what we did is the following. Now these are high speed imaging, because the relaxation process is fairly fast, so you have to go to 500 or 1000 frames per second to probe this. So what we did, we apply step like I showed you, and you get these bright spots which are here, you can see barely. There are only few bright spots. Now what happens if you apply a second step in the same direction? So what we found is if you apply second step in the same direction, this number of bright spots increase actually. And interestingly, the older bright spots still remain. That's why we think that it is a buckling phenomena. It is not like that you are creating new plastic centers in the expense of older one, or older ones are going away. And this is highly directional. Now this I told you that I am applying first step and we are going in the same direction, and you are creating more plasticity. What happens after first step you create plasticity, and if you go back, okay, so that is the second case, you see like you have a lot of plasticity after first step. Now if we go back, immediately you see that if you go in the other direction, the plasticity is gone. So this is highly directional. So, and another important point we need to address, that is a more like long-term thing, is the connection between the relaxation of shear jam system with other dense disordered systems like glassy systems and all, where we also get strongly non-exponential and two-step relaxation. All these things are there, but for glasses it happens typically over much larger time scale. Often the relaxation is not complete, whereas for shear jam system it is happening over a time scale of second. So although both are like dense and disordered system, and they show some overall similarity in terms of non-exponential relaxation, but why this difference in time scale coming, that is very surprising to us. So all the experiments are done by my grad student Sachidanand, and we thank Yatindran for SEM imaging to characterize the particle, and these are my current lab members. And for funding, I'd like to thank RRI and SERB. And if you are interested, so this paper came a few months back, you can take a look. And thanks for your attention.
Thank you, Sayantan. We have about 6 minutes for discussion, so please feel free to ask me questions. Yeah.
Actually, you can hear me. So actually, in the case of like excess stress study which you have done for distinguish between the localized particle for the short time and system spanning for the long time, one comment kind of I was thinking like it could be due to the additive effect which you were kind of remarking in the last, because the time you have done is like initially you have taken some time, the delta t is same, but longer time for the same delta t you are getting more thing. Like I was thinking like it is kind of additive for the throughout the time, and because it is the time origin is not same.
Yeah.
So that's why I was thinking it is kind of.
That's a good point, but that is not really true, because you have to remember that the x-axis is log scale. You are right that time origin is not same, right? So see here, what is the time here? It is roughly 0.2 second. And for example, I take this longest relaxation, so which is 2 seconds. So 2 minus 0.2 is very large. Whereas this first step, it is happening, the total time is less than 0.1 second actually. 2 minus 0.2 versus 0.1.
Yeah, but you showed a image mapping, right? You go a couple of images back maybe. There was a comparison between like a short time back.
Yes. Here also it is the same. See here, because you are confused because this axis is log scale. So here if I take the difference from, let's say, here to here, so this is again 1 or 2 seconds minus 0.1 second, which is negligible. It is like 1.9 second or 0.9 second, versus this first step, it is like happening over everything is happening over 0.1 second. You are correct if this is a linear scale.
No, I understand. I'm not saying it is just additive linearly, not linearly. I'm saying it is coupling altogether, because when
it is coupling,
localized
yes.
for a short time and you are checking again 100 means
Yes,
forgot
yes.
the time scale.
Yeah.
But it is then as a total it is system spanning. Because the time origin is not following up. Like because the delta t was same, but the phenomena was different. For the short initial time when you are checking, it is localized. So it could be like for it is coupling all together, and at the larger time it is
No.
It's not like
So see
this one.
Yeah, this one.
Yeah.
So see here we have taken some relaxation during the first relaxation process.
Right.
So you can take you can shift this time origin. So for example, I can take shorter time. It is not that it will be less. It is not like integrated because after the step actually this picks up suddenly. It is not a like gradually it increases.
But the delta t is same, right? So the time
Delta t
origin
is same.
matters here. So that's what I'm saying. When you are trying
No, what matters is the initial time. What is
initial
your
time, yeah.
initial time?
That's what I meant.
That is the whole point actually, because this is whether you are in dilation relaxation regime or plastic center
And
relaxation.
it was also coupled to the last point you make, maybe the transient state and the steady state. So when you are starting the process, it will directly affect that which state you are in to get that. You might miss the localized part.
Yes. So that is your second point. Is
means
a good one, because see, that is steady state is more very close to that slow relaxation process.
Right. Yeah.
The fast because that is the definition of steady state, right? Like you look at time scale where all the initial things have settled down and system. So typically that is much slower time scale. So that slow time scale becomes correlated with those processes. That is true. Yes.
Thanks.
There might be time for only very short question, maybe.
So I mean, I don't know if you explained like what was the reason, I didn't understand, between why the normal stress increases at the when the I mean, I don't know if you explained that.
Yes. So actually, like, see, you have, I don't know whether board. So you have a dense system, like you have all these particles. Now, when you shear it, actually you have different velocity as you go down, right? Because that is the velocity gradient. Now that means like next layer is going faster than this layer. Because that's why you are having gradient. Now to go like that, the next layer particle has to move over the bottom layer particle, because they are not like point particle, they are finite size, so they have to climb up and like jump like this. So under that condition, there is a like overall swelling of the pack, because otherwise if they are static, you can actually put them maybe in a very nice order, like you don't need to put like on top of each other. But when they cross one another, at some point they have to climb up the particles basically.
So does this depend on hardness? For example, if you emulsion, then the problem will have this.
Yes, no, because you don't have that is a good way, because if you have softer particle, if they can deform, this effect will not be there.
Yeah, we'll take one.
Final question, and
Yes.
then.
Briefly, right at the end you said if you reverse the strain, your plasticity also goes away.
Yes.
So in what sense is that plasticity rather than something that's non-linear elastic? Because plasticity normally by definition is not reversible. So can you clarify what you mean?
Yes, so that is based on the observation, because see, yeah, that's a very interesting point, and honestly we don't understand, because see, the plasticity we are defining by the fact that if you have some isolated bright spot and you load the system in particular direction, you first see that there is accumulation of plasticity along lines, and that line actually, if you keep on shearing, it creates fracture. So now, so if you have accumulated plasticity that is created by deformation, shearing in certain direction, now we found that if you reverse it, those bright spots goes away, and same as like, for example, I'll give you an example that you apply 50% strain Now suppose you go to 50% more in one direction, you create a crack. But now you shear 50% first, and then you apply 50% in the reverse direction. You will never create a crack basically. So in that sense, we are thinking it is an observation, but you are right that plasticity, by definition, it is the irreversible thing. So we don't understand what event can give rise to this.